As I say, I don't know where the check plus plus comes from, but TAs must be getting really, really sympathetic. It's not like the old days. No, but that's check plus plus. Anyway, so we are on seismic work. We're looking at elastic properties. We had a brief introduction yesterday or last Friday about some of the basics of elastic properties and waves. So I'm going to continue on with that. I'm going to just even show you a couple of slides that we had on Friday, just to kind of refresh your memories about what's going on. So here we are. We're at the top of an Earth that we now are thinking about as being an elastic Earth. And the whole concept of having particles inside the Earth that are connected by springs, that's a good thought process to have. So we have some kind of energy source, puts energy into the ground, that comes back up here, it's recorded. That's a control source. It could also be an earthquake. Here's a typical wave recording from an earthquake. The first thing that you see is this P wave, okay? That's a compressional wave where the particles are moving back and forth in the direction of propagation. And we did that kind of experiment up top. And then this is the S wave. Velocities are smaller than P wave velocities. So that's coming in here. And there's some other stuff in here that we're not really sure what is. We'll probably talk a little bit about that. And then there's these big high amplitude events coming in here. Those are surface waves. And we talked about two kinds of surface waves. Anybody remember the names? Yeah, Love and Rayleigh waves. So that could be any of these guys. We had a couple of expressions for the P wave velocity. Expression for the P wave velocity depended upon the bulk modulus and the shear modulus. So shear was the twisting capability, and the shear velocity depends on something like that. So the P wave velocity is always higher than the S wave velocity. Yeah, we sort of did this. We talked about a particle going into, or rock going into water, and then waves coming out. We talked about a wave front that was going through, and also the ray path. So we have a wave front that's like this. We actually could have energy in all different directions. So there's no single ray path that goes with this wave front. There's a ray path that goes everywhere. And so energy that leaves here and arrives here is traveling through a ray path like that. And the important thing is that the ray path is always perpendicular to the wave front. We didn't talk about it. I'll make a mention of it now. Waves decrease in amplitude as they travel. One is because of something called geometrical spreading. So all the energy that goes through this circle must also go through a larger circle, which means if energy is conserved, the amplitude has to decrease. The other is that as we saw when everybody was standing up, remember, like the first person had a big amplitude, and by the time the energy got to the back part, the amplitude was actually really small. That must mean that there's some attenuation that's going on in there, and so energy was being lost. Where'd that energy go? Anybody? So I was pushing up the front. Somebody was moving back and forth like that. He had a lot of kinetic energy. Later on, disappeared.
It would be lost as other forms of energy, like friction or sound, things like that travels through.
Other forms of energy, yeah, and basically converted to heat. So friction, yeah, lost of sound. Probably not so much in that, not in this case, but yeah. So then we have the four different waves: the body waves, as well as the the surface waves, and all had different names and different particle motions. Then we saw this diagram. This was a little movie that's played. So the energy is going off of here, and these are the wave fronts that are propagating through. We can see that there's different things happening in here versus here. So there's energy that's being transmitted into here. There's actually energy that's being reflected from the bottom. And there will be energy. You can maybe see it actually even a bit better. You can see this little blue line? I'm not sure you can see that. I can see it better in this one than I could before. So we're going to spend the rest of the day basically talking about the various aspects of this particular diagram. So first of all, we're going to break that down. We're going to do the direct wave and the reflected wave. Oops. So here was that app. How many people actually downloaded it? And 2 people? 4%. Not bad. Better than nothing. Okay, so you have here's our app, and it's got a layer, one layer up top, another layer, and a layer underneath. So there's 3 layers, and each of those layers has got a particular velocity. So there's a velocity 1, which is 400 meters, velocity 2, 1,000, velocity 3, which is 1,500. So the velocities are continuing to increase. The simplest arrival that we're going to get, so suppose you're sitting at some place, let's say right here. The simplest arrival is going to be something that goes from the shot right to this receiver, and it's going to travel along the surface, and it's the direct arrival. So it's this guy here, travels along here, right along the surface. On the plot beneath, we have what's called the travel time curve. So this is the same distance along this direction, and this is the time down here. And at a particular location, which was 67 meters, the arrival time, which is given by this point here, is about 0.16 seconds. So these plots are kind of companion plots, and we'll be using them a lot. The next ray is going to be the reflection. So this is energy that leaves here, goes down to this interface and bounces back, and we have that the angle of incidence is equal to the angle of reflection. So this reflection point is halfway in between. And the travel time curve for that is something that looks like this. And we talked about this at the end of last day, that as you go far enough away, then the direct and the reflected arrivals come in pretty much about the same time, because they're traveling pretty much the same length in that top velocity medium. So I want to talk in just a second about this reflection. So we're actually going to think about a wave that comes down and gets reflected, or meets this interface. So this is a V1 and this is V2. And this wave is going to come down, and now it meets a medium with different properties. And 2 things happen. Part of it gets reflected, and part of it gets transmitted. But actually, it's not just the velocity that's important here. It's something called the acoustic impedance. So we're going to represent that by the letter Z, or Z, depending on which country you're from. And that's the product of the density and the velocity. So that's the acoustic impedance. So as energy comes down here, the amount that gets reflected and the amount that gets transmitted depends upon that change of the acoustic impedance, and it's given by this formula here. The reflection coefficient is the impedance of the second layer minus the impedance of the first divided by the sum of them. So if I have a wave that's got an amplitude 1 as it's coming in, then there's going to be a reflection. So the wave that's going to come back is going to have an amplitude r, so the reflection coefficient, and the wave that goes down has got an amplitude t. So I've got a reflection, and I've got a transmission, and they're relating to the amplitudes of the waves that just get reflected or transmitted. Now, the interesting thing about a reflection coefficient is that if I looked at this formula here, so that r is z2 minus z1 over z2 plus z1, okay? Let's suppose that I had a medium here that, the velocity is equal to, 100, and I had a medium here that the velocity was actually equal to something that was really big. So let's suppose, suppose 1,000,000. In which case, if I was going to evaluate the reflection coefficient, what's going to be the essential number here?
Close to 1?
It's going to be close to 1. So it's going to be, like 10 to the 6 minus 10 squared over 10 to the 6 plus 10 squared, which is approximately 1. So if I go from a medium with low impedance to high impedance, I get a reflection coefficient of 1. Something positive. And the bigger that difference is, the larger the amplitude. What happens if I go the other way? Suppose that the medium below at a velocity of 0. Then I still have I still have a reflection coefficient but if now my impedance below here is equal to 0, then what does this come out to be?
-1.
So -1. So what does that mean?
Doesn't reflect at all?
Anybody else? If somebody told you the reflection coefficient of a wave was negative, what would you think? Pardon me? Reversing. Yeah. So it's going to change in polarity. So if you can, I'm going to show you this guy here. He works. So here's, oh, what happened? Whoops, sorry. Nice, looks good on my screen. Just a sec. Maybe I have to kill this guy. Oh, that wasn't a good idea. Where am I? No, hold on. How do I get this guy going? I mean, if I go to PowerPoint.
If you right click on it, you should be able to go to it, or you can highlight it. Yeah, you right click on the link. That's fine.
Because in I used to just be able to click on these things.
It's getting finicky. Let's just go to your web browser. Sorry.
Ha. Okay, technology is defeating me. I used to be able to just click on my PowerPoint and it would come up. Anyway, here's the point here. So I've got a wave that's coming in, okay, and there's actually a negative reflection coefficient. So the wave that comes back is coming back with the opposite polarity, and the wave, you can see also that there's still a wave that is going in. So that's the whole concept. I've got energy that's coming in, hit a boundary, some of it comes back, and some of it gets transmitted. And the stuff that comes back is going to depend upon whether I'm going from a bigger impedance, from a low impedance to a high or a high to a low. So the reflection coefficient is either greater or less than 1. Okay, so that was the reflection coefficient. There's also a transmission coefficient that's given by this formula here. So it just depends. It's just 2Z1, whatever the impedance of the first layer was over that. So that tells us now what the amplitude of that transmitted wave was. Okay, so that gives us 2 waves. We've got a direct wave and we've got a reflection. We know something about that reflections. Some of the energy is going to go in and some of it's going to come back. And we also know about the law of reflection. So the other thing that's kind of interesting about waves is that the energy, in a way, if you're sitting someplace, there's some kind of a source, and you're receiving some energy, then you can think about, okay, how that energy got to you by thinking about, okay, what is sort of the minimum energy requirement to get to you, or what is the minimum, let's say in this case, we're talking about travel time path to get you. How does it get to you the fastest? And if you can figure out what the trajectory was that it got to you in the fastest way, that actually tells you how that energy came about. So there's an interesting thing. So we saw something we call them refraction arrivals. And there's kind of an interesting analogy to that happens, I don't know, perhaps you've had it. So imagine that you've got, let's suppose we're down at Wreck Beach. Okay, so here's the beach, right? So here's sand, and here's water. Okay, so now you and your friend are out swimming, okay, and you're a certain length, or a certain distance from the shore. So here's person 1, and person 2 is sitting up over here. Okay, so you're both out swimming. He's over there, you're over here, and then he's in distress, or she. Okay, so let us suppose that you are person 2, and you want to try to save person 1. What's your tactic?
Going to get to them as quickly as possible.
Good. Okay. Now, what would your options be?
You could either go across the water or go up to the sand, which would probably be quicker to move across, and then back down to the water. Perfect.
Okay. So if you went this way, that would be like a direct arrival, right? So you're just going through there. It's the shortest distance, but then what you're really interested in is your travel time, which is your distance divided by whatever speed you've got. And if you're swimming, your speed might actually be fairly small, so this time gets to be fairly large. Okay, so your other possibility is, okay, let's go to the land. Let's go up here. And now you can just haul it across here, right? Because here you have a speed v1, but here you have a speed v2, and you can truck that and go over here someplace and then down. And you might actually do that, right? So you've got travel times to go from here to here, okay? And you got 2 of those, right? So whatever that distance is, let's suppose that's L, so it's 2L divided by V, right? And then you've got whatever X distance you've got across here, divided by V2. But if V2 is large, then that might be small, and you actually might be able to beat him. Right? You might be able to beat the direct swimmer by going up and like this. So that's an important trajectory. We're going to explore that. But the other thing is, like, okay, how do you swim here? Like, what's the best way of doing this, right? So I could just go straight. So I could go straight. That minimizes the distance that I've got in here. So that's okay. And I could come straight back here, but that actually makes this distance here a little bit longer. So now you start wondering, well, wait a minute, maybe this problem is more interesting than I thought. And the question is, okay, what if that's not optimum, and I'm going to sort of slip across here, okay, what is actually the angle that I want to take off from, hit the shore, come back here, and then launch myself again back this way so that I actually get there in the smallest amount of time? So you can appreciate that might actually require a little bit of geometrical thinking for you to actually get a final derivation. But that is the case, right? Because if you just swim straight, that's not going to be the shortest time. If you go too far over here, then that's not the shortest time. So there's got to be some place in the middle, and there's actually some kind of special angle called the critical angle that if you put yourself in that direction, you'd hit the ocean, you'd hit the beach, run across, and get to them the fastest that you can. So we can show that in the app. Let's see here. What do we got? So let us look. So let's suppose we're at, so we're at this particular point. And let's first of all look at the direct arrival. Okay. And then let us look at an arrival then that actually comes down here and then travels along on that interface and then comes back up here. So that's exactly what we were just doing before. And so that would be the first refraction. So now he's coming along like this. And the question is, really, at what point do you win? And we can actually show that by using this guy here. So what is this? So on this side here, so this is time, right? So now I could look at any particular time here. So this is 0.03 seconds. And I look at these wave paths here, and you can see they're partially in solid and they're partially in dashed. And what that means is that at 0.3 seconds, okay, I'm sitting up here. So let's even go earlier. So you see what happens. When we start off, the direct goes this way. The one that's going down is going to be refracted goes this way. So those two are equal lengths. So you're at 0.02 seconds. You've gone the same distance, but he's kind of seems like he's going in the wrong direction. But if you now make this a little bit more, so at 0.03 seconds, you can see this. So now you can see what's happened here, right? So the direct arrival is, you know, plugging along at the surface, but this guy is coming down here and he's actually going a lot faster, and he's getting closer to the end goal here. And you can see this guy. Whoops, is he refreshing? And so now at this point here, you can see that he's up here and this guy is simply way back here. So there's no question that the refracted arrival here is actually going to be first. So now here's the refracted arrival. He's come in. The direct arrival is still way back there. So that's sort of the manifestation of what's happening, and why, as you have these different velocity structures, you can get waves that travel in perhaps a non-intuitive path and actually arrive back where you'd want them to have in an earlier time. The travel time curve looks like this. So this is the arrival times for the direct wave, and this is the arrival times for that refracted wave. There's a couple of things. First of all, we don't get a refracted wave till we're at a certain distance away, so that's called the critical distance. And then once that refracted arrival starts to come in, he's propagating at a particular velocity, so he's got a slope that looks like this. And the thing that we're going to be most interested in is what's called the first arrival. So here's time t is equal to 0, and as we go to these various stations, as we go down progressively in time, we're first of all hit, the first wave to arrive is the direct arrival here. But if we go farther off, then the first wave to arrive is actually the refracted arrival. So what we're going to do is we're going to look a little bit more at this, and then we're going to be able to take these curves here, dissect them, and we're going to do two things. We're going to get the slope of this one to give us the velocity of the upper layer. We use the slope of this one to give us the velocity of the lower layer, and we're going to use this thing here called the intercept time to get the layer thickness. So out of this basic travel time analysis, we can get two velocities and a layer thickness, and that's extremely helpful for a lot of problems, especially when you're looking for bedrock or something like that. Okay. So we've done that. Got your friend out. The one thing that we didn't mention explicitly was Snell's law. How many people have heard of Snell's law? Has anybody had not heard of Snell's law? And what context did you have Snell's law? In optics, yeah. So usually that's where it is. They give you a refractive index of something, and then the light comes in and it bends away. And the relationship between the angle of incidence, which we'll call θ1, and the angle of refraction, which we call θ2, is given by this relationship here, that sine, well, it's the ratio of the sines of the angles is equal to the ratio of the velocities. So what does this tell you? It says that, for instance, we've got so sine θ1 over sine theta 2 is equal to V1 over V2. So if we've got something that's coming in at some particular angle theta 1, and it leaves at some particular angle theta 2, the thing that we're interested in here is like, okay, what is this angle of refraction? So we can just manipulate this. So that just gives us, sine theta 2 is equal to V2 over V1 times sine theta 1. So if V2 over V, if V2 is greater than V1, then this number is greater than 1. So that means that sine theta 2 is going to be greater than sine theta 1 if theta 2 is greater than theta 1. So it's going to, so V2 is greater than V1, this angle is bigger than that angle, so this thing gets refracted away from the normal. So that's how we refer to this, as the angle of refraction, whether it's refracting towards the normal, which is this way, or away from the normal, which is that way. Okay, so that tells us how everything is going to move, and you can see it on this one. So in here, theta or V2 is larger than V1, and you can see here it's coming down like this, and then as you watch the wavefront, it comes shooting out like that. So it's at that angle. Okay. So that's just what we've just said. The interesting thing about this is that because this relationship here holds, I mean, at some point, if V2 actually gets to be large enough, then theta 2 could actually approach 90 degrees. So if theta 2 was equal to 90 degrees, then what's happening? So the energy comes in like that, is now propagating out. I guess so the energy is propagating right along this interface, and that is called a critical refraction. So when theta 2 gets to be equal to 90 degrees, then we've got energy that comes right along here, and we say, oh, the energy has been undergone a critical refraction. The other name for that is that so this energy is now propagating along here, okay? And as it does, so any wave that's propagating along is continuing to put stuff up. So imagine at some little time, just as this wave is hit here, you could think about, it's kind of like an equivalent source that, the wave, something strikes here and there starts to be a wave front that comes off here, and then at a time later, the wave has come across here and it's like this. So as the time goes on, the propagation of the wave has reached this point, but the energy has kind of gone up here. So you get a wave front that is emanating from this surface that's blasting right up to the overlying surface. So you can see this is a straight line in here, and we'll go back and take another look at that movie and see if we can actually see this guy. But this is sometimes it's called the head wave coming in, or the critically refracted wave that is providing energy to the receivers at the surface. Does this help? Can you see this guy? So this was a snapshot of what that movie was. You can probably see it better on your screen. So when you do this on your own computer screen and you watch those wave fronts, if you hit it just at the right point, okay, you see that the wave that's come in here is not, that wave front is way over here. The direct wave that's going in here is sort of sitting up here. And there's this band of energy. It's a straight line, light blue, that is here, and eventually that makes its way all up to the surface, and it arrives first at these stations and then later at these, but it's all propagating with the velocity of this lower medium. Okay, can you see this blue line that's coming from the back? Oh, yeah. So that's our refracted wave. So what's going to happen if the velocity underneath here is less? So suppose that V2 is less than V1. Now what's going to happen? Somebody?
It's going to refract towards it all.
That's right. So it's going to come down and it's going to refract down this way. So this will be theta 2. So if V2 is less than V1, then this quantity here is less than 1. Right? So that means that theta 2 is less than theta 1. So that means it's refracting down this way. So what happened to the refracted wave in this case? Anybody? Somebody. Matt? Who's Matt? Matt, there you are. I'm going to have to learn your names. There's no doubt about it.
You're probably not going to be able to see it on the surface.
Not going to be able to see it at the surface? That's one answer. Anybody else? He's actually right. You don't see it at the surface. Why don't you see it at the surface? Somebody?
It doesn't exist, but it's always being refracted into the same.
That's right. You don't see it at the surface because it never got formed. There is no refracted wave. So in this case, when you're going from basically a high velocity to a low velocity medium, energy gets refracted down, but there is no critical wave that's ever generated. And so it now just looks like this. So the moving, you can just see, there's just nothing happening. You still get a reflection. So you get a direct wave, you get a reflection, and you get energy that goes down, but there's no evidence for what that layer is. That actually turns out to be a really important point, because what you're trying to do, I mean, generally, this is what happens in sort of engineering problems. You've got some layer thickness, you've got a V1 and a V2, and you're generally interested in trying to find out what this layer thickness is, and so you need to know. Well, you're trying to find out what this thickness is, and you're going to do that on the basis of a refraction. So that can only occur if V2 is larger than V1. Now, fortunately, that's usually the case, because this is maybe the bedrock, which has got a lot higher velocities than unconsolidated material up top, and so it usually turns out that V2 is greater than 1, and so you're kind of good to go. But if that's not the case, we're going to be hooped with this refraction analysis. So there's a few visualizations of refracted energy, how it travels through the Earth. I'm not going to show them, but you might just sort of play around with them. It's kind of interesting as you put in different types of velocity structures, just how the waves can kind of move around, and for low velocity zones and things like that. We're going to come back a little bit at the end towards low velocity zones, but fire those guys up, play around with them. Okay, so what I now want to do is kind of turn our attention to really analyzing what we've got, because now we want to turn this information into some real numbers where we've got the velocities and we've got the the layer thicknesses. So here was our ray paths that told us what kind of waves we have, and here was our travel time curves. And now we're going to use the information in here, in particular, the first arrivals, as I said before, to tell us what's there. So just to add a little bit more reality to things, if we have a shot that's going on here, and we have a direct wave that comes along, then we're going to experience that. So let's suppose we've got a direct wave that's traveling. So here's at speed v1. Here's where our shot is, and we're at some distance x from the shot. So at some time t is equal to x upon v1, we're going to get an arrival. And for what we had been doing before, the arrivals were just listed as like kind of a line, sort of an impulse. In reality, what travels is actually not just an impulse, but is something called a wavelet. So instead of seeing a pulse, we actually see some kind of wavelet. We're going to talk a lot about that, but that wavelet could have many characteristics. So it might be something that looks like that, or maybe it looks, something, could even be something that looks like that. What that does is that every time you see a pulse here, then you get a replication of the wavelet that comes in at that particular time, so that the seismic signal that you get is not really an impulse like that, but looks like a replication of this wavelet. So that's why this particular diagram up here shows something that's not just an impulse, but actually has a little bit of a waveform to it. The proper mathematical term is that we're actually going to convolve this wavelet with our impulse response here and generate our seismogram. For now, it's perfectly fine just to kind of realize that every time we would have seen a pulse in the applet, in reality, it's probably going to be some kind of a wavelet of some sort. So that's what's happening up here. The wavelet is kind of looking like this guy over here. And what we have here is a representation of our seismic signals. So here's going to be our direct wave, here's our refracted wave, and there's also going to be a reflection. So we're going to take these guys and break them apart and really try to analyze the specific characteristics of this travel time curve. So first of all, it's just kind of a question of plotting. Let's just start with this. So this is how you'd have seen things out of the app, and you've got lots of stuff that's going on here. But we're only interested in the first arrivals. So what that's going to do, if it does it, gets rid of these guys. So now we've got this, and it's convenient when we work with these to actually kind of flip it up on its end, so that some of the curves that when we're talking about things are actually going to be more looking like this. All that means is we're plotting time this way instead of that way. And you're going to see both of these plots kind of regularly as we go through here. So you just have to get used to the fact that in some manifestations, there's time going down this way, and others we decide to plot up this way. But here's the way I like to plot it from the point of view of thinking about travel time analysis. So we've got first arrivals then that look like that. And these first arrivals, so if we measure them off of here, so here's our seismic plot. So you can see that each one of them now has got this little wavelet on it. And we pick the first arrival. So when the energy is just starting to come up for each trace, we pick this guy, record the time, pick this guy, record the time, dot, 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 and then we plot them up. So at each offset, we plot what the time is. Okay, so that's simple. We get this plot, we look at these guys here, those are our first arrivals, we can measure the time, we plot them up on this graph. We're going to do the same for other arrivals too. So you're always going to be looking for straight lines, because remember when we had a refraction that was coming through, it goes down and then he's traveling along this base at the speed of the lower medium. So he's moving along here, but it's always controlled by what the velocity is underneath. So it's like this, and that means that these arrivals here are associated with this particular rate path. So that means that our first arrivals now could be something now that looks like this. And then if we have subsequent ones, again, we can have refractions from here. We'll look at this case a little bit later. So now I just wanted to take you through these guys. I want to do this. Yeah. So in the GPG, I don't want to do all of the derivations here on the board. They're all kind of done in the GPG. But really all we want to do is the following. We're going to take each of the ray paths that we've got. So we've got the direct wave. And we're going to figure out how much travel time it takes. What is the time it takes to get to a certain distance? And then we'll take and look to see, okay, for this refracted arrival, how much time does it take? And that's, again, easy. This is the swimmer problem, right? So we take whatever length we have in here, divide it by this upper velocity, whatever distance we have in here, divided by the lower velocity, and then another one for the up. So we've got a time down, time across, time up, three pieces of time. We can put them together. We can get an equation for what the travel time is as a function of distance. The one comment that I made earlier was that there was something called a critical distance. So there is a time before which there is no critical refraction. So the first critical refraction is coming down like this. So here's the wave comes down, and then it's going to get refracted across. But by the time it comes down here, it's already out at this distance, and then it's got to get back up. So that means that there's no critically refracted arrival in this point here. And so that means there's a certain distance that you have to go before you see any critical refraction at all. So just one quick thing. So we've got, for our direct arrivals, it's easy. Figure out what the travel time is. It's just the distance divided by the velocity. And for the refracted, I'll go through this in more detail later at the beginning of next week. But I just want to show it just in case it's going to kind of come up in the lab this afternoon. We can also show that the travel time for this wave here has this particular formula, that the time is equal to x divided by v2, which is the distance here divided by the velocity of this lower medium, plus some intercept time. And we have an equation for that. So the reason, and as I say, we'll go over this more in detail next time, but this is how it all works. We go out and we collect the data We measure the arrival times for the direct. So the first arrival times initially gives us the direct. Later on, it's the refracted. The slope of this gives us V1. This is the travel time for the refracted. The slope of that gives us V2. We measure the intercept. The intercept is given by this value here, and that just depends upon the velocities, but we have the velocities, so that gives us the layer thickness. So it's all kind of tied up in one bundle where we do this refraction experiment and we can actually get 3 pieces of information out that are extraordinarily useful. Good.